Now that you've had a chance to play around with some right triangles, you're ready to look at trigonometric functions. So first, we're going to get an overview of trigonometric and circular functions, which is the next big portion of the course that we're going to be looking at. We're going to define 6 of the trigonometric functions eventually by the end of the video. And we're going to show how to compute trigonometric functions for some examples using right triangles. Alright, so first of all, I'm going to explain what trigonometry means, and all it means is these are the study of functions whose origin is the measures of sides and angles of right triangles. And again, right triangles, those are triangles where one of the angles is a right angle, and what I mean by right angle is an angle of 90 degrees or pi over 2 radians. So here we have a right triangle, that right angle in the lower left corner, and we're interested in the lengths of the sides of that triangle. We are interested in the measures of the angles of that triangle. So all those quantities are going to be important to us. So for trigonometric functions, how do we define one? Well, basically what we do is we choose an angle, and we don't choose the right angle. We already know what that one is. We either choose the alpha or the beta from that picture above, and that is going to be, and given that angle, make up a rule that tells us, okay, find 2 of the sides of the right triangle and divide them to find their ratio. So for instance, if I'm looking at alpha, I could say, well, here's a rule for alpha. Look for the non-hypotenuse side of that right triangle that is closest to alpha, and then divide that by the hypotenuse. Well, the closest one to alpha is b. You divide that by hypotenuse, you get b over c. So that is one example of a rule that you can have based upon that angle. Trigonometric functions are super helpful for helping us solve problems involving straight line distances. Anytime you have a problem where you can sort of cleverly draw a right triangle in there to help you, trigonometric functions can be helpful. Once we dip our toes in trigonometric functions, we're going to go right back to chapter 2, and that talks about circular functions. One of the restrictions that we have from right triangles is we can only use the angles that we get from right triangles, which means we can't get an angle of 0 degrees. That doesn't give us a triangle, or let alone a negative value for an angle. That's just nuts. We also can't get a value that's 90 degrees or past, because those angles would be too big for a right triangle. However, for circular functions, we are going to be able to do that. We're going to be able to extend the trigonometric functions past 90 degrees and past 0 degrees as well. And these are going to be helpful for slightly different problems than trigonometric functions. Trigonometric functions are nice for straight line problems. These are nice for problems that have quantities that oscillate and repeat in regular intervals. And we'll show you that when we study sinusoidal functions. So let's start with some trigonometry on a right triangle that you already looked at. You look at the isosceles right triangle. And remember, isosceles is just a fancy word that means 2 of the sides are the same. And of course, you figured out that those 2 sides have to be the non-hypotenuse sides, because the hypotenuse is the longest side of the triangle. And when you used your Pythagorean theorem and some of your common sense, you figured out that the third side was s times square root of 2. That was from good old Pythagoras. And since those 2 angles that are non-right angles are equal and have to add up to 90 degrees, they each have to be 45 degrees. All right, so now I want to look at that angle. I could look at either angle and get the same answers, but I'm going to look at that 45-degree angle in the lower right where my happy face is pointing. And then I'm going to divide 2 of my sides. So again, I have to think of a rule based upon what angle that I have. And my rule that I'm going to do here is I'm going to take the opposite side, and what I mean by the opposite side is the side farthest away from that 45-degree angle. That's going to be the vertical side of the triangle, and then divide that by the hypotenuse. So when I do that, the opposite side has length s, the hypotenuse has length s square root of 2. Very conveniently, those s's cancel to give me 1 over square root of 2. And then I could choose 2 other sides. I could say the opposite side, the side furthest away from the happy face, and the adjacent side, which is the non-hypotenuse side that is closest to it. That's going to give me s over s equal 1. One of the things that you might have noticed about both of these ratios is that the s's cancel and you get the same value no matter how big the triangle is. So no matter what my value of s, it could be a huge number, it could be a tiny number, it's going to give me the same values, which means those numbers are completely dependent on the angles. So again, if I divide any two of those sides, the answer is not going to depend on the size of the triangle. No matter how big the triangle or small the triangle is, as long as the angle is consistent, you're going to get the same answer. That means the answer depends only on the angle of the triangle. So that 1 over square root of 2 and 1 were both telling us something special about 45 degrees and nothing else. So if I have any angle theta between 0 and 90 degrees, and if we have any right triangle where one of the non-right angles is theta. So here's what that picture is going to look like. So there's our theta in the lower right. The opposite side is the one farthest away from theta. The adjacent side is the hypotenuse one that's closest. And then the hypotenuse is, well, the hypotenuse. We're going to be able to define, we're going to define a couple of trigonometric functions right now. Our sine of theta, that is going to be the opposite side divided by the hypotenuse. That's the one we found in the previous slide. And then the cosine of theta is going to be the same thing, except instead of the opposite side, you're going to have the adjacent side. So that's going to be adjacent side divided by the hypotenuse. All right. So one note that I want to make is, again, the size of the triangle does not matter. We can make the triangle as big or small as we want. The only thing that's important is that your angle is correct. And I say angles, and it's kind of important that both angles have to be correct, but most important is that theta has to be one of the angles of your triangle. All right, so let's look at another example that we worked on that first set of activities. The isosceles was the first. The second one was that 30, 60, 90 triangle, and you figured out the three sides to be, well, one of the sides was s square root of 3 over 2. One was 1/2 s, and then the other side, the hypotenuse, was s. And I'm going to look at, I want to find sine theta of like one of those angles, and cosine of it as well. But remember, I can use a triangle of any size that I want. And one thing that you might notice about the two non-hypotenuse sides is they have some unpleasant fractions in there. So what I might want to do is choose a value of s that gets rid of those fractions. And since the denominator has a value of 2, choosing s equals 2 will cancel that 2. So I'm going to use s equals 2, and when we do that, the opposite side, those 2's are going to cancel to get square root of 3. The adjacent side, the horizontal side, the 2's are going to cancel to give us 1. And so here's what we get. We get 1 for the horizontal, square root of 3 for the vertical, and 2 for the hypotenuse. All right, so if I want to find sine of 60 degrees, I can use this triangle. I love this triangle. It has no fractions. Now, sine, remember, is the opposite divided by the hypotenuse. The opposite is the one that's farthest away from 60 degrees. So that's going to be the vertical one, which is square root of 3. The hypotenuse has length 2, so that gives me sine of 60 degrees. Now, if I want to find cosine of 60 degrees, now I'm looking for the adjacent side. So that is the non-hypotenuse side that is closest to 60 degrees. That one is 1. And then the hypotenuse is still 2, so I get 1/2. Now, I can use this same triangle to find sine and cosine of 30 degrees as well. Except my notion of what opposite and adjacent are going to be a little bit different. Because if I'm finding sine of 30 degrees, I want to find the side of that triangle that is farthest away from 30 degrees. That is no longer square root of 3. Now it's 1, right? 1 is the furthest away. Same hypotenuse, though. That's 2. For cosine, my adjacent is going to be the one nearest 30 degrees. That's no longer 1, right? 1's the one that's furthest away. The non-hypotenuse side that is closest to 30 degrees is square root of 3. The hypotenuse is 2. And so cosine of 30 degrees is square root of 3 over 2. Now, we have a couple of other trigonometric functions. And when I say a couple, what I really mean is we have 4 more. We have 6 altogether. Because you can define a trigonometric function with any two sides of that right triangle. And, whoops, you can do it in any order, right? So, and there are 6 ways that we can do that. We've already done 2 of those ways, right? So anyway, here's our triangle. We have theta, we have our opposite side, our adjacent side, and our hypotenuse. So we've already done sine of theta and cosine of theta. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. For tangent, we're going to ignore the hypotenuse and just look at the opposite and adjacent sides. That's opposite divided by adjacent. For cotangent, we're going to do the exact same thing, ignore the hypotenuse, except we're going to divide them in the opposite order. So instead of opposite over adjacent, we do adjacent over opposite. Now for secant of theta, we're going to do exactly what we did for cosine actually. For cosine, we did adjacent over hypotenuse. Secant of theta, same two sides. We're just going to do it in the opposite order. And then the last one is cosecant of theta. We're going to work that one just like sine of theta, except we're going to switch the order of the opposite and hypotenuse. So cosecant of theta is going to be hypotenuse divided by opposite. All right, so now that you've had this introduction to trigonometric functions, you get to work on the activities that says that exact same thing. Introduction to trigonometric function. That's on the PDF included with this video.